All right, guys, today we're going to start Chapter 8. Chapter 8 is all about hypothesis testing. And today is just some of the basic things. What a hypothesis is, how we state our hypotheses. We're going to do some things like find some critical values, things like that. Tomorrow we're going to get into the actual running of an entire test. So today is just kind of some of the basic intro-y stuff for you is all. Getting familiar with some of the terms, if you will. When we talk a statistical hypothesis, it's a conjecture about a population parameter that may or may not be true. Now, I know you guys outlined these ahead of time, but remember, parameters are things dealing with the population, things like population mean, population variance, population standard deviation, population proportion. So when you see parameter, those are the types of things that we're talking about. So we're going to make a conjecture about maybe population mean. That's what we're going to start with tomorrow. But that's what we mean by parameter. There's two types of hypotheses for each situation, for each hypothesis test we run. The first one is called the null hypothesis. It's symbolized, it's H, and that's a sub-zero. That's a subscript of 0. And that will always state that there's no difference between your parameter and a specific value, or there's no difference between two different parameters. So there's no difference between population mean and a specific value. Like we think the average test score on the ACT is 22. So my specific value in that case would be 22. And we'd be looking at the population mean for our parameter. The other hypothesis is the alternative hypothesis. It's symbolized with a capital H and a little subscript of 1. That hypothesis will state some type of difference between a parameter and a specific value, or between two different parameters. And so by a difference, we might think that our mean ACT score is greater than 22. Or we think that our mean ACT score is less than 22 or something like that. So there's going to be some type of difference there. That's where we express the difference will be in our alternative hypothesis. Oftentimes it can be referred to as the research hypothesis because the researcher, the one actually conducting the study, that's often the thing that they are claiming. Often, not always, but often they're claiming that there's some kind of difference there. Not always going to be the case. Your null hypothesis and alternative hypothesis, they're stated together, just like you see in the table below. A null and alternative, you need both for each test that you run. The null hypothesis, if you look at the table, it always has the equal sign. The null hypothesis states there's no difference. So by no difference, we're saying that it's equal to that specific value. The K that you see, I had a few people ask me about this when they were outlining yesterday. They're like, Miss Golly, where do we get that K from? What's the deal with the K? The K is just the specified value. So I'd said we think the mean ACT score is 22. K would become the 22. Whatever the specific value is that you're hypothesizing that parameter to be. That's where K will come in for you. There's 3 different types. We see a two-tail, a right tail, and a left tail. And those are just determined by the symbol that you find in your alternative hypothesis. The null hypothesis is always going to be an equal sign. So that doesn't help us out much differentiating between the 3. So you look at the alternative hypothesis. For a two-tailed test, the alternative hypothesis is always a not equal sign. The right tail, left tail, here's the cool thing. How do I tell which is which? It's the way that the inequality symbol points. So notice for a right-tailed test, the inequality symbol points to the right. For a left-tailed test, the inequality symbol points to the left. So it's the way that the symbol is pointing which will determine which tail our test is in. And we're going to make this visual in just a little bit, so sit tight. If you're like, Miss Golly, what do you mean by left tail, right tail, two tail? We are going to see the distribution in just a few minutes, so sit tight. The claim is what the researcher is trying to actually show. So the researcher might claim they think that the average ACT score is 22, or maybe they're claiming, we think the ACT score average is less than 22. So it's the idea that the researcher is trying to show. So your evidence can only support the claim if it's in the alternative hypothesis, and it can only reject the claim if your claim happens to be the null hypothesis. And that's something we're going to see more tomorrow when we actually get into performing one of our tests all the way through. We'll see it a little more tomorrow. So let's just take a peek at our first example. This is on the handout that I gave you. We have scores on a standardized test have a mean of 70. Some modifications were made, and now an educator believes that the mean might have changed. We want to state our null and alternative hypotheses, and then determine if we're right, left, or two-tailed test. Now, how much you write, I have the explanation I'm going to go through. I have the wording up here for you if you want to, since it's just the start of this for you. It's your first shot at doing this. If you actually want to be able to jot down the explanation behind it, that's why I put it up here for you, okay? So we have, for our null hypothesis, the null hypothesis is always going to state that there's no difference, no change. So the mean that we have, we're given is 70. So we always start with our symbol for the null hypothesis, which is our H sub 0, and then a colon. Be careful. Today, since we're just starting off with things, everything's going to be about the mean. We have to make sure that we have the correct symbol in our hypotheses. The same way we had to make sure we had the correct symbol in our confidence intervals last chapter. We have to make sure we have the correct symbol for the parameter we're dealing with. So we're going to have no change in the null. Alternative hypothesis, H sub 1, followed by a colon. We're dealing with the mean, so we have mu. And now the educator believes that the mean may have changed. The educator doesn't say specifically how they think it's changed. They just think it's different. Okay, they don't state, oh, they think it might have decreased or they think it might have increased. Just said, well, we think it changed. So all we can do for the alternative hypothesis is to do a not equal. So all we're saying when you put a not equal there, all you're saying is it's something different than that 70. If you have an equal and a not equal for your two symbols, that is when you have a two-tailed test. Now there's nothing special with that one. I can't say, oh, it's the way a symbol points like we can for right and left tail. So it's kind of that process of elimination. You don't have an inequality symbol pointing left or right. So all you have left is two-tail. That's how I remember those. So what I want you to do is just take a minute. You guys have two more examples on your sheet. Just take a minute here, take a little pause here, and try out those other two. Just write your two hypotheses, and then see if you can tell which type of test you have, right, left, or two. Now, at the very least, get the symbols down. If you're unsure of everything else, you're thinking, oh, I don't know which way the symbol should go in the alternative, at least get the symbols down. Get the H sub 0, get the H sub 1, get the mu's in there. At least try those out. All right, let's see how we did. In number 2, you have the mean monthly rent for an apartment was $800. And I know today we're focusing on the mean, but I just want to make sure we know why we're using the symbols we do in our hypotheses. So we're looking at the mean monthly rent, $800. There's a real estate agent that believes the mean rent is higher this year. State the appropriate null alternative hypotheses. Here we go. So at the very least, I'm hoping you could at least get that far. You've got the symbols for the null and the alternative hypothesis, and we know we're dealing with the mean, so we're going to have a mu there. At the very least, I'm hoping we got that far. The null hypothesis is always going to contain the equal sign, and we're looking at $800 for our mean this time. If the mean rent is higher, which inequality symbol is going to work for that? Greater than. Inequality symbol is pointing to the right, so we're going to have a right-tailed test. It's all about the way it points. That's how I like to remember it. If you want to remember when the alternative is a greater than that it's to the right, I think that takes a lot more effort than just remembering which way the symbol points. Totally up to you though on that. There is also, and when you guys start doing these yourself, Just a little reference for you. It's in the section 8.1. On page 416, there is a table of common phrases for hypothesis testing, and it shows you which inequality symbol they would go with. So for example, the upper left part, it has the greater than symbol, and then it gives phrases like is greater than, is above, is higher than, is longer than, is bigger than, is increased. So it just gives you a bunch of different phrases that you would then in turn put a greater than in your alternative hypothesis. So if inequality symbols, if you're kind of shaky on what phrases might give you each of those, page 416 might be something you'd check out. Okay, and you don't have to do that right now, but I'm just saying as you start trying more of these on your own. Example 3, you have some boxes of cereal labeled containing 20 ounces. The inspector thinks the mean weight might actually be less. Again, at the very least, I'm hoping we have the symbols for each hypothesis. We're looking at the mean, so we're going to use mu. Null hypothesis always has the equal sign, and now they're thinking the weight might be less than, so we're going to use a less than and the value of 20. The value, that numerical value that you have in your null hypothesis, always matches the alternative. So if I have a 20 in the first one, I have to have 20 in the second one. They'll match. Inequality symbols pointing to the left, so we do have a left-tailed test. Okay, this will be your very first step when we actually do our full-out hypothesis test tomorrow. You have to state your null and alternative hypotheses. So after you do that, we have to pick out the correct statistical test. And all that's meant by picking out the correct statistical test, it's similar to our confidence intervals. We had to evaluate it and see, were we going to do a confidence interval? Did we have to use Z or did we have to use T? What type of test did we have to run? It's going to be very similar with our hypothesis testing. Are we evaluating it for the mean, for proportion, for variance? What are we looking at? And then once you have your test selected, you have to find your appropriate significance level. So that's how we're going to finish up today, is looking at those couple things. Statistical tests, again, we're going to have a different one for a mean versus a proportion versus a variance or standard deviation. And all that the test does, we're going to use data from our sample to figure out if we should or should not reject our null hypothesis. And hypothesis testing, that's always going to be your end result. Did you reject the null hypothesis or not? It's all about rejecting or not rejecting the null hypothesis. Doesn't matter which thing you're claiming. It's all about when you run the test, what your result is if you're going to reject the null or not. That's what the end result will be. There's 4 possible outcomes when you decide to reject or not. The first type is you end up rejecting the null hypothesis when it is in fact actually true. This is a type 1 error, and that'll be symbolized by alpha. We're already a little familiar with alpha. The second possible outcome is you reject the null hypothesis and it actually is false, so it should have been rejected. Third option is you don't reject the null when it's true, and again, that's a good decision, that's the correct one. And number 4, we do not reject the null hypothesis and it's actually false. When that happens, that's a type 2 error, and it's symbolized with kind of a goofy capital B looking thing, which is beta. So again, those are the 4 possible outcomes when you run your hypothesis test. You might not always come up with the correct conclusion. Your level of significance, that's your probability that you're going to actually commit a type 1 error, so that you end up rejecting the null hypothesis and it's actually true. So what percent, what's the maximum probability, or percent if you will, chance that you are going to commit that type 1 error, that you're going to reject the null hypothesis and it's actually true. And we already alluded to this. We symbolize that level of significance as alpha. And there's 3 arbitrary significance levels. Remember, guys, we had to find alpha. We worked with z sub alpha over 2. We had to find alpha. And remember, to find alpha, if we had a confidence level of 99%, to find alpha, we did 1 minus 0.99. They match. Confidence level 95%. To find alpha, we did 1 minus our 0.95. So those arbitrary significance levels, those alphas, those are the same three that match up with our confidence levels from our confidence intervals. They match up. Those are the big three. Those are the big three. But again, not the only three. The other piece I do want to tackle today is finding what's called your critical value. And these make a little more sense when we can make them a little more visual. The basic idea for us, your critical value, the ones we're going to look at today, we're going to use table E. We're going to find z-values. That's what we are definitely most familiar with. And what the critical value does on our distribution is it separates the area where we're going to reject the null hypothesis from the area where we won't reject it. That's what the critical value does. It separates, here's when we're going to reject versus here's when we won't reject. That's what those ideas, that's what those critical values do for us. And we already kind of alluded to the idea of like a right tail, left tail kind of test. When you have those one-tailed tests, the left tail, right tail, your critical value, there's just one of them. It's either on the right or the left, whichever type of tailed test you have. The null hypothesis, and we're going to look at this more tomorrow, will reject it if it falls in the rejection region. Two-tailed test, you're going to actually have two critical values for that. We're going to see that in just a minute. We're going to make this more visual. Two-tailed test, you're going to have two critical values. You're going to have two rejection regions. Now, I know it's kind of hard. We've just been talking about it. It's a left tail, it's a right tail, it's a two-tail. What the heck does this look like? Well, so I wanted to start with, this is our standard normal distribution and our z-values, if you will. And when you have, this would be, this top one is a left-tailed test. So notice the left tail of the distribution is shaded. That shaded region is our rejection region. So tomorrow when we run our test and we get a test value, we're not going to run any tests today, but when we get our test value, if our test value falls in that shaded region on the distribution, we reject our null hypothesis. If our test value falls in the non-shaded region, we don't reject our null hypothesis. Here is where our critical value would lie. And it depends, your critical value, just like our z sub alpha over 2, it's going to depend on what your alpha level is, that significance level. This area, I'm just going to go ahead and label rejection region. And then the non-shaded stuff, non-rejection region. They should be called critical and non-critical regions. But for me, it's all about rejecting or not rejecting the null hypothesis. So the shaded stuff I say is the rejection region, the unshaded is the non-rejection region. And again, tomorrow we're going to run a hypothesis test, the full deal. We're going to get a test value, and depending upon where it falls, shaded region we reject, non-shaded region we don't. That's going to be the idea. Below that, you see a right-tailed test. Inequality symbol points to the right. The right tail is shaded in. Critical value is off to the right. So the right tail, left tail, it's referring to where we're going to find those critical values and critical rejection regions on our distribution. For the two-tail, notice for the two-tail critical values, they have a plus minus. So there will be two different critical values, and they will be equidistant from the mean, aka the middle. Two-tailed test, because both tails are shaded in, you have two rejection regions. So if your test value, when we come up with that tomorrow, if it falls in either of those, you would reject for either one. So again, I know that this is all new for us, the idea of writing those hypotheses. I'm hoping, though, that this makes the idea of left tail, right tail, two-tail a little more visual for you. So then tomorrow, when we run the test, we get our test value, at least we have some kind of an idea how to write our hypotheses and how to draw our diagram. So to finish up today, what I want us to find, and these are on the back side of your handout, I just want to go through how to find those critical values. And this is actually something you are already really, really familiar with how to do. That's why I wanted to do the standard normal distribution today. So left tail or right tail test is going to tell us where our rejection region is. So this is the left tail test. So I'm going to shade that left tail. And now I need to find that critical value, and since we're at the standard normal distribution, it's going to be a z-value. You're going to find the z-value that separates the shaded from the non-shaded. Now, the nice thing with this is alpha represents the area of your rejection region. Alpha represents the area of your rejection region. So you don't have to do 1 minus anything. You don't have to divide by 2. Not yet, anyway. That's just the area. Now, you guys all showed me on your last test, you can find a z-value when you know the area. You guys all showed me that you had to define the sample sizes. So it's the same idea. You have 2 options. Look up our 0.1 in table E, or on the calculator. I know more and more of you were picking up the calculator. We go the opposite. But again, either way, whether you're a table person or calculator person, you have to know the area to the left of your z-value you're trying to find. You have to know the area to the left. This one should come out to be, and you can double check whichever method you like, should be negative 1.28. Should be. The left-tailed tests, those are definitely the easiest ones to find because they give us, here's the area to the left. So knowing the area to the left makes finding those critical values a lot easier. So let's talk two-tailed. I started with what I thought was the easiest. Now we're going to get progressively the order I think they are from easiest to toughest. A two-tailed test. The alpha value is the area of your rejection region. So if your rejection region is split into 2 parts, what are we going to have to do with alpha? Split it into 2 parts. So, the area in each tail is just going to be 0.01. So for a two-tailed test, you do have to divide alpha by 2, because alpha is the area in our rejection region. Well, if that rejection region is split into 2 tails, I have to split alpha between the 2 tails. I recommend, guys, find the left one first. Find the negative one first. So you can go table E for 0.01 or a calculator for 0.01. Totally up to you what you like to do. However you found your z sub alpha over 2's on the last test, that's what I would stick with for these 2. This one should come out to be, and you can just write it with a plus minus. Those are equidistant from the mean. So if you find the negative one, you can find the positive one. What I got for this one? 2.33. And again, if you're a calculator person, let's just stay consistent and let's round to the nearest hundredth. Let's just stay consistent and round to the nearest hundredth. The last type of test is our right-tailed. And I saved what I think is the more difficult one. You're going to have to decide how you like to handle the right-tailed test the best. Alpha is the area in the tail, in that shaded region. If I use table E or if I use the calculator, 0.005, it's not going to get me that positive z value. If I put 0.005 in my calculator, that would put me at a left tail test. So what you have to be careful of, we need to do 1 minus. Whoops. This will be the area that's the area to the left of the critical value. So you can look up that area in the body of table E, or you can put that area in your calculator. Now, I know for some of you, like, but Miss Golly, if I put 0.005 in my calculator, or I look that up in my table, and if I get Z equals negative 2.58, can I just take the negative sign off and use that? And the answer is yes. So if you want to use 0.005, if you want to look that up on the left side of your table, or you want to put that in your calculator, you will get a negative Z value. You just have to remember, though, and this is the only part that worries me a little bit, you have to remember to take that negative sign off, though, before you make your comparisons when we're going to reject or not reject. So how you want to handle finding critical values for a right-tailed test, that's up to you. Do you want to do the 1 minus and get that area to the left? Or do you want to use alpha and just remove the negative sign from the Z you come up with? Totally up to you. Just to finish up, before we actually dig into the hypothesis testing tomorrow, these would be all the steps for hypothesis testing. Stating the hypotheses will do. Steps 2 and 3, however, this is more of an introductory type stats course. The designing of the study, the conducting, the collecting of data, we talk a little bit about how to maybe collect the data, some of the sampling techniques, things like that, but we actually don't get into the designing and the actual conducting and gathering. If and when you have to take another stats course, then that's what you get more into. That's the piece you'll get more into. We don't get to do that, unfortunately, because I think that's the very interesting part is when you actually get to do it yourself. We will, though, we will do number 4. We'll evaluate the data we're given, decide whether to reject or not, and we will summarize the results. So what it will look like for us, and again, we're going to dig in with our first test tomorrow for population mean. We will state the hypotheses and identify the claim. We will find critical values, these 2 steps. We should hopefully be already comfortable with by the time tomorrow comes. Compute the test value, we'll do that tomorrow. Make our decision to reject or not, and then we'll summarize the results. Now the summary part, though, make sure if you didn't include in your outline, there is a great summary table on page 425 that helps you get familiar with how to state your summary. So we're going to reject or not reject the null, but then the summary part, we have to go back and look at what our claim actually was. And what does rejecting or not rejecting mean for our claim? So that piece we'll get into a little more tomorrow, but the nice summary table, though, is found in this section. So just want to make sure you have that reference back for you guys.